This episode of Metatrex is brought to you by Enterprise in Space. Find out how you can help science and education and become a virtual crew member aboard the NSS Enterprise Orbiter. Visit enterpriseinspace.org for more information. And if you'd like to help us keep Star Trek discussion coming to you each day, consider becoming a patron of the network through Patreon. Visit patreon.com/trekfm and find out how you can become part of the team. That's patreon.com/trekfm.
This is Tim Russ, Lieutenant Commander Tuvok on Star Trek Voyager, and you're listening to Trek FM.
There's no greater challenge than the study of philosophy.
My philosophy is that there is room for all philosophies on this station.
Welcome, everyone, to episode 54 of Metatrex, Trek FM show on Star Trek and philosophy. My name is Mike Morrison, and with me, as always, is Zachary Fruhling. Today, we're going to be discussing paradoxes of motion in the Star Trek universe, from Zeno's paradoxes to the twin paradox in Einstein's special theory of relativity. Zachary, you are looking particularly perplexing today. How are you?
Why, thank you. Well, I'm looking forward to talking about paradoxes today because paradoxes are one of these things in philosophy where you either really kind of geek out on trying to solve the logical problem and figure out what went wrong with the reasoning that leads to some sort of paradoxical result, or you're likely to just dismiss them out of hand as some sort of sophistry or something that you don't need to take seriously. So I actually have fun talking about paradoxes because while I don't find them the deepest issues in philosophy, they're not as deep as, say, ethics or metaphysics. It can be fun just as an intellectual exercise to kind of walk through the reasoning process that generates these paradoxes and see if you can pick them apart and try to figure out what went wrong with the reasoning. So I'm looking forward tonight to talking about the Star Trek themed version of the paradoxes that we're going to talk about. You know, all the paradoxes we're going to talk about tonight are paradoxes that came up in the history of philosophy or in the history of science. And we could definitely tell the boring run-of-the-mill version that everyone else talks about, but I'm looking forward to telling the Star Trek-themed version of these paradoxes today.
Yeah, without a doubt. You know, the thing that I find so much fun about paradoxes, by their very nature, are ridiculous. They're absurd. They really are full of absurdities. In fact, by definition, you know, a paradox is logically unacceptable. It's self-contradictory. That's, you know, by definition what a paradox is. And so I enjoy the frustrations of how these things tend to circle back and contradict themselves. And I've always found that fascinating as I've studied various paradoxes over the years. I know when we were first talking about this, I was looking forward to talking about some of the paradoxes of motion. For instance, you would have, in the history of philosophy, you would have something like Achilles and the tortoise. And just kind of giving that its own sort of Star Trek spin, we could liken that to, say, the Enterprise D and the Franklin. The Franklin, of course, being the first ship to go warp 4, and then you have the Enterprise D that has the ability to, you know, travel at warp 9.9 as a comfortable cruising speed. So I'm looking forward to this.
I think the thing that's so frustratingly seductive about paradoxes is that the reasoning that generates paradoxes, when you first start out through the reasoning process, seems to be really good. You follow a chain of reasoning that seems really plausible, and then you realize that it leads to some absurd, unacceptable result, and hence the paradox. You know, oftentimes these paradoxes lead to a result that is obviously false, so blatantly false that it defies things we know from common sense. So you know there's something wrong with the reasoning process, but then the challenge is to kind of reverse engineer the reasoning and figure out where exactly you went wrong. Which crucial step of that reasoning is the problematic step that leads to that absurd consequence, when each step in the reasoning is seemingly innocuous or seemingly plausible.
And the fun thing here, Zachary, is that neither you nor I are experts in the field of paradoxes. So this is going to be fun.
Just in my everyday life. I live a life of paradox. I don't know about you.
Well, again, there's plenty of absurdity in my day-to-day life. So in that, I definitely have experience with paradoxes, but I'm by no measure an expert. So this will be fun as we grope our way around talking about paradoxes. And as you and I talked in the Turbo Lift, we're not really going to talk so much about paradoxes within Star Trek because although there are some, it's difficult to pin a specific episode of Star Trek on some of these paradoxes we're going to talk about. But who knows? As we're talking, maybe something will pop up that we didn't anticipate. But nevertheless, it's going to be fun.
Yeah, I think with a couple of the paradoxes we're going to talk about, you would be very hard pressed to find an actual example of a paradox right inside Star Trek. I mean, other than time travel paradoxes, which we're not going to talk about today. We're talking about paradoxes of motion. On the other hand, you can find everyday run of the mill situations that you encounter inside the Star Trek universe that would be affected by these paradoxes. They're just run of the mill situations like moving your ship from point A to point B or firing a photon torpedo. Those kinds of things are subject to the paradoxes that we're going to talk about. So the fun that I'm going to have, I think, is just in telling the Star Trek themed version of the paradoxes, not so much as trying to find examples of the paradoxes, strictly speaking, inside the Star Trek universe.
Well, let's dive in and talk about Zeno and the Arrow paradox.
So the ancient philosopher Zeno gave a series of paradoxes that have collectively come to be known as Zeno's paradoxes, more specifically Zeno's paradoxes of motion, because they all involve the absurd conclusion that motion is problematic or motion is impossible. So one of Zeno's most well-known paradoxes of motion is called the Arrow paradox. But because this is a Star Trek and philosophy podcast, we're not going to talk about the Arrow podcast. I decided to term this one the photon torpedo paradox.
That's appropriate.
So my Star Trek themed version of the Arrow paradox, or the photon torpedo paradox, goes something like this. You can divide time into smaller and smaller and smaller units. Like in a period of time, if something is moving, like say you're in a ship and you fire a photon torpedo towards another ship, it takes a certain amount of time for that photon torpedo to go from one ship to the other. And you can divide that period of time into smaller and smaller and smaller units, in which case the photon torpedo is going a smaller and smaller and smaller distance. And if you think of time as something you can keep decomposing into smaller and smaller units, you can ask yourself, well, what about an instantaneous moment? Not a period of time, but literally a single moment that doesn't have duration. And if you can keep dividing time into smaller and smaller and smaller units to the point where you get down into an instantaneous moment, then at that instantaneous moment, the photon torpedo doesn't cover any distance. It hasn't moved. It's stationary in that instantaneous moment. And if you think of a duration of time as composed of an infinite series of infinitely small moments that don't have duration, just like you would do in calculus, taking a limit down to a certain value, the limit as the duration goes to zero. If time is composed of an infinite series of these infinitely small moments, then at any given moment, the photon torpedo is not moving. So that's the paradox, that motion should be impossible because at any given moment, the photon torpedo is not actually moving in those infinitely small moments. And all duration is a series of infinitely small moments with no duration.
So that's how the Baku do it.
So Mike, it sounds like you generally agree with Anish that it doesn't have to take centuries to learn to live in an infinitely small moment.
Evidently not. I think we should actually call this the insurrection paradox, really.
And his fist be ever ready for a knockdown blow.
Here's a cool thing about this. When you think about it, when you break it down, it's ridiculous, and yet somehow this makes sense, Zachary, because you can divide time in such a way that there is a moment in which that photon torpedo is motionless. I mean, after all, if it's occupying equal space and everything's at rest, you can divide that time down to the point to where that photon torpedo is not moving. There is no locomotion happening.
We'll talk about the reasoning here in a minute and why this paradox leads to an absurd conclusion. But just dwell on the fact that it's an absurd conclusion for a moment. The conclusion is basically that motion is impossible. But obviously that's wrong, right? You look around the world and you see things are in motion, things are moving. How could that conclusion be right? And that's exactly the nature of a paradox. The paradox is problematic completely because it contradicts our everyday experience, right there. This is an absurd conclusion that we should not accept, and yet it's hard to figure out what exactly is going wrong with the reasoning. And so that's the challenge with the paradox is, okay, we know this conclusion is absurd and doesn't match up with our experience and is obviously false based on what we see in the world around us, but where exactly did it go wrong? So it's not, the point of a paradox is not to take the conclusion seriously. The point of the paradox is to recognize the fact that it doesn't match up with our experience and try to reverse engineer the reasoning and say which step in that reasoning was the problematic step. So Mike, you actually mentioned a second ago that you found this plausible, that you can divide time into progressively smaller and smaller and smaller units to the point where you get to an infinitely small unit. And that seems to be the step that in this case that generates the paradox.
Yeah, because unlike Zeno's other paradoxes, rather than dividing space, we are dividing time. And so it's unique in that sense. And when you think about it in those terms, it can almost seem plausible. I'm not saying it is. It's ridiculous. It's absurd. It's nonsensical. But when you think of it in terms of dividing time, it can almost seem plausible.
I think there are at least a couple of things you can say about what's wrong with this paradox, the photon torpedo paradox. I think one objection right off the bat is that as you divide time into smaller and smaller and smaller units, you never get down to an infinitely small unit. You can always keep dividing that further and further and further and further. You never get down to a slice of time that's infinitely small. You just get smaller and smaller and smaller. You go from half a duration to a quarter of a duration to an eighth of a duration to a 16th of a duration, and on and on and on you go. But at every step, you never get to an infinitely small slice. You never get to an instantaneous moment. Each of those moments just has a progressively smaller and smaller and smaller duration. And the crucial step in the photon torpedo paradox, or Zeno's arrow paradox, seems to me that Zeno seems to be claiming that you get to a point where you get an instantaneous moment with no duration whatsoever. But as we've kind of described dividing up time, you never get to get down to an instantaneous moment. You get down to very, very, very tiny moments that themselves have very small durations, but not a duration of zero, not an instantaneous duration.
Yeah, indeed, because it no matter what increment you're able to slice that piece of time down into, that photon torpedo is always going to be moving. There's no way to come to an absolute zero where the photon torpedo is without motion. There's always going to be locomotion, because in terms of the photon torpedo being in motion, it's always in motion. So there is no absolute zero and breaking that down in time. But in theory, certainly one would think that you could.
So that's one way of attacking this. I think you can attack this problem from a purely quantitative, numerical, arithmetical standpoint. I think you could also attack this a couple of ways from a physics standpoint. I think one way you could attack this from a physics standpoint is to argue that if you talk about the properties that an object has, its spatial properties, like it's located at a certain point in space-time, right? Mm-hmm. It has coordinate X, coordinate Y, and coordinate Z. That information itself doesn't exhaust all of the properties that an object has. An object also has momentum, and that if that's one of the properties of an object, albeit a relational property in relation to other objects in space-time, if that's one of its properties, then Zeno seems to be claiming that as you drill down into smaller and smaller time units, you can sort of strip away this idea that an object has momentum, that it's moving towards or moving in relation to other objects in space-time. But I think from a physics standpoint, you could plausibly say that that's one of the essential properties that an object has. It's a relational property, but this paradox seems to amount to ignoring that an object has momentum in space-time, that it's in motion. And of course, that's the point of the paradox. It says no, it doesn't. It's if you drill down to an instantaneous moment, it doesn't have momentum anymore.
Well, Zachary, going back to my point about insurrection, and I kind of like the parallel there that we drew. I don't know if we've made the case that this is the insurrection paradox as opposed to the hummingbird paradox. But visually, I have to say that it increases my appreciation for that scene in Insurrection, in that never at any time, even though they referred to it as freezing time, never at any time did everything freeze in the moment. They referred to it as stopping the moment, freezing the moment, but everything was moving incredibly slow, but nothing ever really stopped. And so that just increases my appreciation for the visual elements of insurrection. And I think there's a correlation there between this particular paradox and what we saw in insurrection.
Well, Mike, as I think of ways you can try to attack the arrow paradox or the photon torpedo paradox from a physics standpoint, it occurs to me that physicists themselves have a conception of the smallest unit of duration or the smallest unit of time. And it's generally whenever philosophers start talking about physics, the physicists kind of roll their eyes and go, oh, no, not these philosophers. They don't really understand what's going on. And to some extent, that's true. I don't understand the mathematics, and I'm not a physicist. I'm kind of a well-informed layman when it comes to physics. But generally, if there's a concept of the smallest unit of duration or the smallest unit of dimension, then there's some you can kind of use that as an objection to this paradox, the arrow paradox or the photon torpedo paradox. If it's not possible to divide time any further beyond a certain point from a physics standpoint, whatever the reasoning is behind that concept, then that's an objection to this paradox. You can't keep dividing time down into that infinitely small moment with no duration.
Yeah, it occurs to me because the end result obviously is for the photon torpedo to strike its target. And in Zeno's paradox, the idea is that if the photon torpedo has hit its target, it's not in motion because it's already there at some point in time. And the only way that I can imagine a photon torpedo not being in motion and hitting its target is if perhaps maybe the transporter chief beams it aboard. But even still, we're moving photons, we're moving matter, we're just doing it in a data stream.
Mike, I'm trying to think of ways to help our listeners visualize this paradox, trying to think of an instantaneous moment with no duration. And the example that comes to mind is the example of the episode Timescape from The Next Generation. Mm-hmm. If you remember, in that episode, time is actually frozen. Captain Picard and Counselor Troy and company are in their own in normal space-time, but the Enterprise time has been sort of frozen in a particular moment. And they walk onto the ship, and everyone's frozen in a moment. There's a phaser firing that's in the moment, and everything is essentially stopped. And of course, in that episode, time isn't actually stopped. We just find out that it's running very, very slowly to the point where a warp core breach is in process, and it's going to happen over a period of hours as opposed to fairly instantaneously. But that scene, just the general gestalt of what's happening on the ship there, with everyone kind of stuck in their places. Motion, things that are in motion are just literally frozen in time. I think that's an example of what Zeno had in mind, that if you think of time as a series of instantaneous moments, and in that episode, the time on the Enterprise has essentially stopped, ground to a halt. You're stuck in a particular moment where things that are in motion are not actually in motion anymore. And that is a great example of this paradox, because if you think of time as a series of instantaneous moments, if you look at any one of those moments when time is just ground to a halt, then nothing is moving anymore. And that's essentially what you see in the visual depictions of what's going on in the Enterprise in that scene.
Yes, Zachary, plenty of time for Captain Picard to draw a smiley face and the smoke coming off the warp core reactor breach. It also takes me to a Voyager episode, Blink of an Eye, in which Voyager is caught actually in orbit of a planet in which time is moving at a different rate. And so when the inhabitants of that planet come to Voyager, they're moving at a much faster rate. And so it appears that the crew of Voyager are motionless.
And I think that neither of these two episodes, neither Blink of an Eye nor Timescape, are a perfect example of what Zeno has in mind for this paradox. Because the paradox really does rely on a truly instantaneous moment in time, not just a slow duration of time, not just a different reference frame, not just time moving at different rates, but a truly instantaneous moment where there's no motion whatsoever. But I think the visual depictions of what's going on in those episodes give you a great example of what that would be like. Imagine an instantaneous moment with no motion. Zeno's point is that if you look at just a single snapshot of a moment in time, not a duration of time, then there's no motion. And so as you go from moment to moment to moment, how how does that motion occur if all time consists of is a series of these infinitely small moments? How does motion ever occur? Of course, he reaches the absurd conclusion that motion never occurs, which from our point of view is an absurd conclusion. And I think this idea of breaking time down into an infinitely small moment with no duration isn't very plausible, given that you can keep dividing time in smaller and smaller and smaller units. His primary assumption that time is made up of a series of infinitely small moments with no duration is probably the problematic assumption that leads to this absurd conclusion. So rest easy, starship captains and tactical officers. You can still fire your photon torpedoes, and they will, in fact, hit their targets as long as you aim well.
So talking about dividing time and going from the ridiculous to the even more ridiculous, let's talk about Zeno's dichotomy paradox. And since most of Zeno's paradoxes we're actually getting secondhand, primarily from Aristotle, Aristotle says that which is in locomotion must arrive at the halfway stage before it arrives at the goal. Okay? So an example might be Homer walking to the end of a path.
So, Mike, since Aristotle's retelling of Zeno's dichotomy paradox involves walking a great distance, I was trying to think of examples from the Star Trek universe where characters are walking a great distance. And the example that came to my mind was the Next Generation episode Final Mission, in which, if you remember, Captain Picard and Wesley Crusher are, hitching a ride with Captain Durgo from the shuttlecraft Nenebek, and they crash on this planet and they have to walk to the mountains. So they have to walk a great distance. So I decided to call this one not the dichotomy paradox, which is a mind-bogglingly boring name, but I decided to call this one the Nenebek Paradox, which, as we know, the shuttlecraft Nenebek is named after our good friend of the network, Larry Nemecek.
And now Larry has a paradox named after him. Larry, there you go.
Talk about influence right there. He has a whole paradox named after him now. The Nenebek Paradox. Years from now, centuries from now, they're not going to talk about Zeno and the dichotomy paradox anymore. They're going to talk about Larry Nemecek and the Nenebek Paradox.
Totally.
So this paradox, I think, is actually a bit easier to understand than the previous paradox, the photon torpedo paradox. In the Nenebek paradox, so in order to walk a great distance, in order to walk from the shuttlecraft Nenebek all the way to the mountains, the first thing you have to do is cross half of that distance, right? And you can't walk all the way to the mountains without crossing half of the distance first. And that takes a certain amount of time. But in order to cross half of the distance, you first have to cross half of that distance, or a quarter of the distance between the shuttlecraft Nenebek and the mountains. But in order to cross a quarter of the distance, you have to cross an eighth of the distance, half of that distance, and so on and so on and so on. And obviously, since you can keep dividing this down into smaller and smaller units, a 16th, a 32nd, a 64th, and so on, the paradox goes something like this. Because you can't do an infinite number of things in a finite amount of time, motion should be impossible, because in order to cross a certain amount of distance, you have to cross half of that, and then half of that, and half of that. And that's eventually an infinite number of things. If you keep dividing that into smaller and smaller and smaller units, you get an infinite number of distances that you have to cross. And the intuition behind the paradox is that you can't do an infinite number of things in a finite amount of time. And so motion should be impossible. And again, the point of a paradox is not to take that conclusion seriously. It's that's an absurd conclusion. Motion is obviously possible. Obviously, Picard and Wesley and Captain Durgo can walk to the mountains, right? But the paradox leads to this absurd conclusion that motion isn't possible because you can't do an infinite number of things or cross an infinite number of distances in a finite amount of time.
As I think about it, Zachary, I think about the final mission. We kind of are drawing a little inspiration from that particular episode of The Next Generation. There's a really great picture in there when we're talking about traveling distances, and breaking those distances down, in order to get to the other side of the desert, or whatever the journey is that you're taking. Maybe we're warping to Risa or whatever,
or trying to get home from the Delta Quadrant,
or try to get home from the Delta Quadrant. You have to, in order to get all the way there, you have to first get halfway there, and to get halfway there, you got to get a quarter there, and to get a quarter there, and so on and so forth. And you're breaking down these little slices of distance. And as I think about the final mission, there's this really great picture in there. When you think about it, Captain Picard says to Wesley, "Oh, I envy you, Wesley Crusher. You're just the beginning of the adventure." And that is coming from Captain Picard, who, seemingly is halfway there. I think it's probably fair to say at this point in his career. He still has some distance to cover, but he sees Wesley Crusher at the beginning of the event, at the beginning of the adventure, and he envies him in some way. Here's someone, beginning the journey, and Captain Picard, who's already traveled that first halfway length. I think it's kind of an interesting picture in there that I think to some degree folds into our example that we're talking about.
Well, Mike, I think it's actually a little bit harder to know what's gone wrong in the reasoning in the dichotomy paradox or the Nenebek paradox compared to, say, the arrow paradox or the photon torpedo paradox. I think that it's a little trickier to figure out what's gone wrong with this set of reasoning. In fact, it's probably something that in the 24th century, every grade school person would be able to figure out, because as we know from the Next Generation, every grade school student takes calculus in the 24th century, right? We learned that in the Next Generation. And actually, it was calculus that was really needed to figure out what's wrong with this paradox. In calculus, you can find out that an infinite number of things can actually add up to a finite number. And this is the concept of the limit, that as you make those distances smaller and smaller and smaller, those can actually add up to a finite time or a finite distance. And that's something that was counterintuitive to ancient thinkers, but as a result of Newton's work on calculus, we can figure out the solution to this paradox, that even though you have an infinite number of distances, as you think of dividing this distance into smaller and smaller chunks, half and then half and then half. Each of those distances is actually smaller and smaller and smaller, progressively smaller, to the point where if you add them all up into a mathematical series, you can end up with a finite distance that you can in fact cross in a finite amount of time. So it was actually calculus that was needed to figure out the solution to this one. But like I said, in the 24th century, every grade school kid knows calculus, so this paradox is ancient history by the time the 24th century rolls around. So much for Larry Nemecek's legacy with the Nenebek paradox.
Sorry, Larry.
By the 24th century, this paradox is ancient history.
Well, Zachary, it seems like that there are some similarities between the Nenebek paradox and the Enterprise D and the Franklin paradox, or as it's known in its proper terms, the Achilles and the tortoise example in Zeno's paradoxes of motion. I see some similarities there. In Achilles and the tortoise, Achilles allows the tortoise a 100-meter head start, for instance. And the idea is that Achilles would never be able to overtake the tortoise by dividing time. It's the same principle, or dividing space rather. It's the same principle, except we're talking about a foot race between Achilles, who obviously is much faster than a tortoise, or the Enterprise D, that is certainly much faster than the Franklin at warp 4.
That's the thing, Mike. All of these Zeno's paradoxes really rely on some sleight of hand when it comes to dividing up time or space into smaller and smaller units. In the first case, with this photon torpedo paradox, we came to realize that maybe it's problematic to realize that you get an infinitely small moment of time based on dividing time into smaller and smaller units. And in the Nenebek paradox, even though it's mathematically possible to keep dividing a finite amount of space into smaller and smaller units, cutting it in half at every turn, turns out, because of the mathematics of calculus, that actually adds up to a finite distance, even though there's an infinite number of progressively smaller units of distance in that infinitely long series. Both of those paradoxes seem to rely on just some interesting sleight of hand with mathematics and division, and frankly, neither paradox is very convincing. And that's the whole point of a paradox: is both of these paradoxes lead to an absurd conclusion that is rejectable out of hand. But it's a little difficult to know exactly what went wrong with the reasoning in these paradoxes.
And frankly, we get much the same with Achilles and the tortoise, or the Enterprise D and the Franklin. It's again, calculus kind of lays that to rest, and so we lay the Nenebek paradox to rest. And so, Zachary, we move from the Metatrek's Nenebek paradox to Einstein's twin paradox.
Well, as we were planning out today's show, I thought it would be really interesting and fun to juxtapose these ancient paradoxes that we've been talking about, Zeno's paradoxes, what we've jokingly called the photon torpedo paradox and the Nenebek paradox, with a much more modern 20th century paradox, the twin paradox from Einstein's theory of relativity. And that's a huge gap in time. We're talking a gap in time of thousands of years. And I guess my point in juxtaposing these paradoxes together was to show that even though these ancient paradoxes lead to absurd consequences, the problems with motion by no means have been solved by the 20th century. Even in the 20th century, a physicist like Einstein was coming up with a new paradox that people had to think about and had to resolve with the help of physics and philosophy. And these are open issues. Even though the ancient paradoxes seem a little absurd from our modern perspective, given what we know now with calculus and whatnot, motion is continually a problem. This isn't an issue that has kind of gone away. So for people who aren't familiar with the twin paradox, this paradox arises as a result of the fact that time slows down the faster you are moving. And this is something that is really counterintuitive if you didn't know this or haven't taken the time to think about it before. And it definitely contradicted with what we thought we knew about the physical world as a result of Newton's physics, Newton's laws. So one of the things that's hardest to understand about Einstein's theory of relativity is the notion that there's no absolute reference frame for space-time. And we're used to thinking about space and time in a very objective kind of way, that space and time are out there and they're fixed, and objects move around in them very much like billiard balls or photon torpedoes going from point A to point B, but space just kind of being fixed and present and static in the background there, the environment in which objects move. But we learned from Einstein's theory of relativity that that's not how time and space actually work. That as objects move through space at a certain velocity, time actually slows down, and objects that have gravity or objects that have mass actually end up warping space-time around them. So this malleability of space-time, the lack of an absolute reference frame, means that each object in space-time has its own velocity and its own perspective, its own reference frame, if you will. And that leads to some really seemingly absurd consequences. And one of the most well-known absurd consequences is the twin paradox. But because this is a Star Trek podcast, we're not going to talk about the twin paradox. We're going to talk about the Delaney twins paradox, or the Delaney sisters paradox. So I kind of wrote up this Delaney sisters version of the twin paradox. But before we talk about that, let me just give some sense of what the twin paradox is. So one of the most interesting features of Einstein's theory of relativity, as a result of the lack of an absolute reference frame, as a result of the fixed speed of light, is that the faster you move through space, the slower time actually goes for you in your reference frame. And that is something we don't deal with in day-to-day life, right? We're not moving at velocities that are very rapid. We're not moving close to the speed of light in any way, shape, or form. So the relativistic effects just don't affect us here in day-to-day life. So what's interesting to me is the way space and time actually work according to the theory of relativity. They just don't match up with our day-to-day perceptions of space and time. And this is kind of this mental shift you have to make when you start thinking about the theory of relativity. You almost need to make sure you're checking your own assumptions about how space and time actually work, and for the sake of running with the examples. But because this is a Star Trek and philosophy podcast, I decided to not talk about the twin paradox, but I thought we could talk about the Delaney sisters paradox. I thought that would be a lot more fun to talk about than some generic twin paradox.
Well, and again, Zachary, to go back to something we referenced earlier, I see some similarities between what we're describing here and what we saw on screen in the Voyager episode Blink of an Eye, because they were moving at two different speeds. The planet was moving at one speed while Voyager and the rest of the universe was moving at an entirely other speed. And so, again, the reference point for the people on the planet was that the things around them weren't in motion. What seemed like a mere hour for the Voyager and her crew was eons in the history of this species that was observing them, the sky people.
Well, the basic idea behind the paradox, before we start talking about the specific example, I have a much more specific example involving the Delaney sisters that we'll talk about here in a minute. So before we start talking about the specific example of the Delaney sisters paradox that I mentioned, I thought we could spend just a minute talking about the just the overall twin paradox. Like, why is this even a problem? So the idea is that if there's no absolute reference frame and two people are moving at different velocities, like say someone stays here on Earth and then someone else leaves planet Earth traveling at a great velocity, something approaching the speed of light, the person moving at a great velocity, time would actually go slower for. But because there's no absolute reference frame, from the perspective of the person who's traveling, it actually looks like it's the Earth that's traveling far, far away and moving really rapidly. And so from the perspective of the person moving, it should be the time on Earth that's actually slowing down. So it leads to a paradox because it seems like from each person's perspective, time should actually be moving slower for the other individual. But obviously they both can't be true at the same time. And that's kind of the paradoxical result, that those two things aren't consistent with each other. So there has to be a way of resolving this paradox and not leading to this absurd consequence that each twin is getting older from the other person's staying younger from the other person's perspective. That's an absurd consequence, and that's why this is called the twin paradox. That consequence is absurd. So I thought we could just drill down a little bit and talk about a slightly more specific example of how this actually works out, including just a little bit of easy to understand math, but using the Delaney sisters as an example. So here's my Delaney sisters retelling of the twin paradox. Are you ready for it?
I'm ready for it.
Okay.
The Delaney dilemma.
The Delaney dilemma. I love it. That rolls off the tongue a little better than the Delaney sisters paradox, the Delaney dilemma. You could set that to a little clarinet music, and you'd have a great song title.
Hey, I like it.
Yeah, that's the B-side to Echoes of the Void, the Delaney dilemma. Harry Kim and the Kim Tones, the Delaney dilemma.
The Delaney dilemma.
Okay, so here's my Delaney sisters paradox. Suppose that Jenny Delaney remains on Earth while Megan Delaney, and remember, Megan Delaney is the one with the cute little dimple, and I put her on Voyager for Harry Kim's benefit. Suppose she leaves Earth aboard Voyager, going at impulse speed, traveling really fast, something approaching the speed of light. Let's call it 0.6 times the speed of light, and they're moving towards a star that's about 6 light years away. So from the perspective of Jenny Delaney back on Earth, it will take Megan 10 years to reach the star that's 6 light years away. Remember, they're moving at 0.6 times the speed of light, 0.6 light years. And so it'll take 10 years to reach the star. But from the perspective of Megan Delaney aboard Voyager, the star actually appears to be only 4.8 light years away. And this is due to a couple of things. It's due to the constant speed of light, and it's due to this thing called length contraction, or what's called the Lorentz contraction in special relativity. The idea is that as you're moving towards an object, from your perspective, moving at a certain velocity, things actually get compressed as a result of the constant speed of light. And distance, as it's measured from the perspective of someone who's moving in a certain direction, distance actually gets compressed. So actually, from the perspective of Megan Delaney moving at 0.6 times the speed of light, the star is actually only 4.8 light years away if that were measured from that perspective. And so if you're moving at that velocity, from Megan's vantage point, it'll take actually 8 years to get there instead of the 10 years that Jenny perceives back on Earth. So suppose that both of the Delaney sisters set their chronometers to 0 before the trip to try to keep themselves in sync and reconcile this paradox. And also suppose they can perceive each other. So suppose they have a subspace telescope or a radio telescope or even a light telescope where they can see what's going on from the other person's standpoint. When Megan Delaney reaches the star, Megan's chronometer reads 8 years. And remember, that was because the star was only 4.8 light years away instead of 6 light years away from Megan's standpoint because of this Lorentz compression or this Lorentz contraction. But when Jenny sees Megan reach the star from her own perspective back on Earth, her chronometer actually reads 16 years when she actually sees through her telescope that Megan has reached the star. And why would it be 16 years? You have to kind of spell this out a little bit. Well, it would be 10 years for Megan to make it to the star in the first place, because from Jenny's standpoint back on Earth, the star is 6 light years away. And it would take 6 years for the light to reach Earth, right? So if you're putting yourself in Jenny's standpoint, by the time she actually sees Megan reach the star, it would be 16 years according to her clock. So according to Jenny, Megan's clock is actually running at half speed because, again, by the time Megan perceives herself as reaching the star, it's only been 8 years according to her clock, but it's been 16 years according to Jenny's clock back on Earth. So now on the trip back, Jenny views Megan's chronometer going from 8 years to 16 years in only 4 years' time, since her chronometer was at 16 years when she saw Megan leave the star, and it will be 20 years by the time Megan arrives home. And why, again, 20 years? Well, it's because from Jenny's standpoint, stationary on Earth, it's 10 years there and it's 10 years back. So a total of 20 years by the time Megan actually reaches home. But if you remember from the perspective of Megan, who's actually making the journey and feeling the effects of this Lorentz compression, it's 8 years for each part of the journey, 8 years to the star and then 8 years back to Earth. So at the end of the trip, this is kind of the paradoxical counterintuitive result. At the end of the trip, both Megan and Jenny Delaney agree that Megan's chronometer reads 16 years while Jenny's chronometer actually reads 20 years. And so the counterintuitive result, the paradoxical result that each twin perceives the other's time is going slower is actually reconciled, because if you kind of walk through the mathematics and walk through the, what each person is perceiving, the person who's actually making the journey to the star and coming back, time actually does move slower for that individual, and that clock would be running slow by the time the return trip is made.
Yeah, you've got two completely different inertial frames there.
Exactly. I think what's interesting about thinking through the example like this with the Delaney sisters is that it seems to resolve the paradox. If you remember, the paradox was that each twin should perceive the other's time as moving slower as a result of the lack of an absolute reference frame, right? From the perspective of the person on Earth, the person who's traveling is the one who has velocity. From the perspective of the person who's traveling, it's actually the Earth that seems to be zooming away at a rapid rate. And so it seems like from each person's perspective, time should be moving, the other person's time should be moving slower. But if you walk through the reasoning and kind of add up, who's perceiving what according to their clocks and perceiving what on the other person's clocks, it turns out that the person who travels to the star and then comes back, that person's time is actually the person's time whose clock is moving slower. And both participants in the thought experiment can actually agree on the result and thereby resolving the paradox or eliminating the seeming contradiction.
One of the things that we're dealing with in this paradox, Zachary, is the concept of gravitational time dilation. And that's actually something that is quantifiable in science. We have, at least experimentally, produce results that indicate that time dilation is a real thing. And it surprises me that we never really deal with this in the Star Trek universe, at least in terms of, how we're talking about it with the Delaney twins. We never really, again, you go back to the Voyager episode we mentioned previously, but to really look at this problem in the Star Trek universe, we never really even address it. We just kind of wave a hand at it and that's it, unless perhaps maybe one of our listeners out there can think of an episode or an instance in the Star Trek universe in which they address this to some degree. But I can't think of a single example in Star Trek in which we see this addressed in any way, shape, or form in Star Trek.
Yeah, and I'm frankly really surprised because this is something that is generally accepted by the scientific population.
Yeah.
They have trouble reconciling special relativity with quantum mechanics. That's still work that theoretical physics needs to do. But special and general relativity are very, very well accepted premises of the scientific community at this point. So it's surprising that Star Trek, which is a science fiction franchise that invokes so much high-speed travel, and this doesn't apply at warp drive. I'm even granting the fact that warp drive counteracts or somehow undermines the effects of special relativity, that this time dilation effect doesn't affect travel at warp speed. But at impulse speeds, when you're moving a significant fraction of the speed of light, something approaching the 0.6 c or the 0.6 speed of light that we used in the Delaney sisters example, I'm surprised that Star Trek hasn't dealt with it pretty much at all. And like you, I can't think of a single case when Star Trek really dealt with the time dilation effects of special relativity head on and incorporated that into a story. I think what's interesting to me, Mike, is just how incredibly different the reality of space and time is with things like special and general relativity compared to our intuitive sense of the reliability and the evenness of time. According to special relativity, time is something that's malleable. The faster you move, the slower time goes. And just dwell on that for a minute. If you haven't taken the time to think about this before, if this is your first time really thinking about what that really means, the faster you move, time actually moves slower. So this is kind of like time travel into the future, right? If you can move at a significant fraction of the speed of light for some significant time and then return back to Earth, time is actually moving slower for you, which means more and more time is passing on Earth. This is essentially a well-established well-established way of doing time travel into the future. If you could go fast enough, which we can't because we have a hard time accelerating to those speeds, but if you could travel at a significant fraction of the speed of light, you could essentially travel into the future. Time would progress more rapidly on Earth than it would for you moving rapidly. And that's a very interesting, very practical, well-accepted method of time travel into the future. So there is a way of time traveling into the future. You just have to go really, really, really fast, something approaching the speed of light. And if you haven't...
slingshot around the sun.
Or slingshot around the sun. We learned that in Star Trek 4. Yeah. So like you, Mike, I just find it really interesting that a franchise like Star Trek that is so willing to entertain abstract ideas and, fringe scientific ideas and speculative science and speculative philosophy, that they haven't dealt with something as well established as the special theory of relativity. And again, we really want to emphasize this is something well established, right? This is something that the scientific community in general accepts. It's even been experimentally verified by taking atomic clocks up into the space shuttle or in the International Space Station at a great velocity and showing that when the clocks when the clock that's been in space comes back to Earth, the atomic clocks are out of sync with each other. This is not even like bad mechanical clocks. These are atomic clocks that become out of sync. So this is something that's been experimentally verified time and time again, well established. And it's something that leads to some really strange consequences, like this twin paradox. That if one twin goes off into space at a great velocity and comes back, that twin would actually be younger than the twin that remained on Earth. So if you're feeling your years, if you're feeling a little up there in age, staying on Earth is not the right thing to do. You need to get yourself on a starship now.
And Zachary, we've been able to quantify time dilation in circling particle beams in particle accelerators. So again, this is real science here. This is real quantifiable science that we don't even get. I mean, we don't even get a hand wave, I don't think, in the Star Trek universe. And again, we might be able to say, well, that's
the time ship relativity does not count. Let me just say that right now.
Captain Braxton, I'm sorry, but it doesn't count. But that is the Delaney dilemma, listeners. So
to recap, we have the photon torpedo paradox. We have the Nenebek paradox, a little nod to our friend Larry Nemeczek. And we now have the Delaney dilemma or the Delaney sisters paradox.
There we go. We have redefined science as we know it, Zachary. I think our work here is done.
I think it's a heck of a lot more fun to think about these paradoxes in Star Trek terms. And again, we don't have a lot to say about these paradoxes. I mean, the first two paradoxes, Zeno's paradoxes or the photon torpedo paradox and the Nenebek paradox, you can really kind of dismiss out of hand as a result of some very bad reasoning about dividing time and space into smaller and smaller units. We've pretty well established that reasoning is problematic. What I think the twin paradox in Einstein's special theory of relativity is much harder to reconcile, because if you ditch the concept of an absolute reference frame, then the conclusion that each twin perceives the other as the one that's moving is a very plausible conclusion to reach once you ditch the assumption of an absolute reference frame. So what's wrong with that? And of course, as you walk through the reasoning, and of course, as you take into account the actual research and the actual experiments that have been done with time dilation, you can realize that there is no actual paradox. It's still a counterintuitive conclusion, the idea that clocks that are moving end up going slower, and that as you move more quickly, you age more slowly. That is still a counterintuitive result that doesn't match our everyday experience. But it's not a paradox because all the participants can agree on what the outcome should be, and you don't end up with a contradictory conclusion like you might have guessed, given the perception of each twin's perception of the other once you ditch the concept of an absolute reference frame. So the paradox is essentially resolved, but it's much harder to know how to resolve it than it is with the two Zeno's paradoxes that we talked about. Well, Mike, it's been fun talking about paradoxes of motion in the Star Trek universe. And of course, you know me, I'll take any chance to talk about the Delaney sisters. So I'm glad we got the Delaney sisters paradox in there. But this isn't the only thing we've been talking about here on Trek FM this past week. So here's a quick look at some of the other things you may have missed elsewhere on the network.
Previously on Trek.fm, Earl Grey.
And then as kind of a teenager, I kind of drifted a bit from Star Trek, and I pretended one time when I went to see Star Trek Nemesis that I was actually off to see Elf instead, because that sounded cooler than seeing Star Trek Nemesis. Maybe it still is.
To the journey!
Maybe even playing it with Tuvok, who I think will be brilliant at it, and then it just constantly going brr, brr, and him just getting really annoyed. Yeah.
Tuvok would be the Operation Champ.
Yeah, he would. Yeah.
See, and then the evil holographic doctor from Equinox is singing, the reticular nodes connected to the...
Yes.
Warp 5.
We should get Larry Nemeczek on, and we should do a supplemental episode where we just talk and we act like we're Tellarites and we just insult each other for the whole episode.
You would probably love it.
What do you think? I think it's a good idea.
Yeah, I don't know. That would be... I might have to get coached by our listeners.
Meta Treks.
And that's the world of language that we live in. It's not this purely referential sense of language. Like when Riker says a minuet, he doesn't just mean, oh, yeah, that thing minuet that I can point to, whatever that is on the holodeck, right?
The 17th century French dance. Maybe he wants to dance.
Riker wants to bust a move.
And that's what else is happening on Trek.fm.
Check out these shows and find out what we're talking about in your favorite corner of the Star Trek universe and beyond. You'll find us wherever you get your podcasts. If you're an Apple user, be sure to hit the subscribe button. That helps us out greatly, and it makes it easier for other listeners to find the show as they search iTunes. If you're not an Apple user, we've got you covered as well. You can find our shows on Stitcher, TuneIn, SoundCloud, Windows Phone, and of course you can stream and download the MP3 file from our website and grab the RSS link as well. Another way you can help us keep all of our shows coming to you each week is to become a patron of the network on Patreon. If you visit patreon.com/trekfm, that's patreon.com/trekfm, you'll find our current goals and different milestone contribution levels, along with all the great perks we have for you. These perks include early access to content, exclusive content, producer credits, seats in our content development team, and many more. We really appreciate any support you can give us, and we hope you'll join the team. Again, you'll find all the details at patreon.com/trekfm. And don't forget to check out Enterprise in Space, a project of the nonprofit National Space Society that will design and launch an 8-foot orbiter and return the craft to Earth. The NSS Enterprise orbiter will carry more than 100 student-designed science experiments into space, and you can help make it happen. Visit enterpriseinspace.org to find out more and to get your seat on the mission. If you'd like to contact us with feedback or suggestions for the show, or to send us your thoughts on anything we discussed in this episode of Metatreks, you can contact us in several different ways. You can contact us via a form on Trek FM's website. Just go to trek.fm/contact.
We'd love to hear your voice. Leave us a voicemail. Just look on the sidebar of the show page or go to speakpipe.com/trekfm.
On Twitter, you can find us under the handle @TrekFM.
On Facebook, you can find us by going to facebook.com/trekfm. And while you're there, please check out the Babel Conference. Just type the Babel Conference, that's BABEL, into the search field on Facebook, or go to our website at trek.fm and click discussion on the menu bar. That is our listeners only discussion group. It's a closed group, but if you click to join, one of our administrators will let you right in.
We also invite you to leave a rating and a review of Metatreks on iTunes. We'd love to hear your feedback and suggestions for the show. Well, Mike, when you're not passing the time counting an infinite series of instantaneous moments, where can our listeners find you on the interwebs and around the Trek FM network?
Well, Zachary, they can certainly find me around Facebook. That's where I'm most active, and in the Babel Conference. On Twitter, my Twitter handle is @cmichael1701. I'm also on Instagram, cmichael1701. You can also catch me on recent episodes of The Ready Room and Warp 5. And Zachary, when you're not hanging out with Megan Delaney traveling 0.6 times the speed of light, where can our listeners find you on the network and around the interwebs?
You mean Megan Delaney and her dimple, right? Well, you can find me elsewhere on the Trek FM network as co-host of To the Journey, Trek FM's Voyager podcast, along with Kay Shaw and Suzanne Williamson, my co-hosts on that show. You can find me on the Babel Conference, Trek FM's listeners-only discussion group, if you want to talk about Star Trek and philosophy with me there. And you can find me on Twitter. My handle is just my name, @Zachary Fruhling. That's Zachary, ZACHARY, and Fruhling, FRUHLING. Well, we'd like to take a moment to acknowledge the rest of the Metatreks team from the network. Specifically, we'd like to thank C. Brian Jones, the founder and publisher of Trek.fm, our executive producers, Matthew Rushing and Kenneth Tripp, Aaron Harvey, our art director, Richard Marquez, our production manager, and our Patreon manager, Brandon Shea Mutala. And we'd like to give a special thank you and a shout out to our 3 associate producers here on Metatrex. We'd like to thank Patrick Devlin. You can find Patrick under the Twitter handle @MagicDrop5. We'd like to thank Kay Shaw, who likes to talk Voyager with me over on To the Journey. You can find her under the Twitter handle @ChocoWeeble. And Norman Lau. You can find Norm under the Twitter handle Starfighter1701. Well, everyone, thanks for listening to Metatrex, a Star Trek philosophy podcast. Until next time, when we will once again boldly go where no philosophers have gone before.